The Chordophone. There are many similarities with the what's called aerophone. Any class of musical instruments in which a stretched and vibrating string uh, produces the initial sound. Any class of musical instruments in which a stretched vibrating string produces initial sound. The strings, if we have some open tube here, and we have acoustics of a spring, and an open tube or string. It should be string. We have, for instance, we have here a wall, and a pulse coming this pulse here, and then it hits the wall here, and then it changes its phase, yeah, and then come here and turns the other way, this way, and further this way, yeah, and yes, so it's the same as with an open acoustics for a stretched string is the same as for a it's called open cylinder. We have the speed here. C is same adiabatic constant times the atmospheric pressure and the air density, and it's for a tube, and for a string it is C is the tension in Newton divided by T tension in Newton, and mu is the mass per length. We will use it later. Yeah. Okay. So maybe I should. Okay. F, the frequency F for a natural frequency is like this, and it is the same as C divided by 2L, or the effective length times this. Yeah, it's 1 over CDL, or 1 over 2L, and it could be written as 1 over 2L times the square root of T divided by M P times yes, so it is times the mass density. Yeah, and that is the same as times T divided by P times rho, and this form comes up here. The square root of one of the fours, it gives 2, so this makes 2 over like this. So it's another no 2. It should be 1 over. I'm a little bit sloppy now. It should be L times D like this. Okay. And yes, so mu is the same as rho pi diameter squared divided by 4. Okay. And the acoustics of a string, all the notes, and we have, as I told you, an open cylinder is like a string in both ends. String in both ends, it is closed there. Yeah. Okay. And yes, and we have the same. We have the open tube here, and we learned that that the the motion should be like this, and the what's called the pressure should be like here. There's a mode for pressure means a note for, for motion. Yeah. And now we have a string here. A string is like here, attached in both two ends here, and we have it's like that. And this is the length L. Yeah, this is a half length. Yes. Yep. So it and we can have for the string, we can have all the frequencies like here. N is 1, and then we can have like this. Oh, there were too many. Shit, there should be n is equal to 5 here. Yeah. Yes. And you can say that for the natural frequency, an open source, there's not a clear pitch percept, but for a string, more clear pitch percept. It's like here. Yes, like this. It's, oh, more sharp. Yes. And then we have, if we have a piano, how to make it? Where F is, as we know, 1 divided by 2 L, like this, and can also be written as we saw, 1 divided by L times D, the length, and what's called, now I got it, this. And the notes discuss how to design a piano. Yeah. Yes, because it turns out that if you keep T constant, and if you make mu constant, it makes if you the lowest one is from 75 Hertz to 486 Hertz. So it shows up that this frequency, this ratio is about 152, is the same as L for low frequencies divided L for high frequencies. So if a string 10 centimeters goes to be 15 meters. You can also L and density constant. What then? So it shows up again that L and then it's the L and this rho is constant. So it shows up that again we get this fraction so, and that means that D low to D high is that a ratio. So that means if you have a 1 millimeter, it comes to get 15 centimeter in diameter for a string. And then in a harp, we still have in a harp both L, the length L, and the diameter is varied. So harp is right here, harp vary L and diameter. Yes, we can vary in a very what's called, we can vary D and the mass density in Bandura. Okay, then we talk about some other things, deviations. The spring is not totally fixed at both ends. That could be not fixed, and the string can be inhomogeneous, and so also an effect of the fretboard. If for instance on a guitar there is a height difference between the what's called saddle and the bridge. Yes. A string also has some stiffness, and a totally flexible string is not good, because a string needs to transmit energy to the bridge. Okay, and we can have some inharmonicity. So we get instead of Fn Fø, we get now Fn is n times Fø times a term like this, n minus 1 times B, where B is inharmonicity. It's a little bit complicated term. Deviations not fixed, and some what's called the other one, string inhomogeneous, and the third one a fretboard, and the last one was stiffness. Yeah. So there are different kinds of bridges for violin, banjo, and guitar, and also sitar. There's some space. It's called the Javari.